The minimum size of bare copper conductor permitted for encircling a building in a direct burial grounding application, as specified by the National Electrical Code, is number 8 American wire gauge. This translates to a conductor diameter of approximately 8.37 millimeters. This requirement is essential for ensuring a reliable and effective grounding system, which plays a critical role in electrical safety. A grounding system provides a low-impedance path for fault currents, allowing protective devices like circuit breakers and fuses to quickly interrupt the circuit in the event of a ground fault. This helps to minimize the risk of electrical shock and fire. The number 8 American wire gauge minimum size is not arbitrary. It is based on calculations and testing that take into account the potential fault current levels, the soil resistivity, and the desired grounding impedance. Using a conductor smaller than number 8 American wire gauge could compromise the effectiveness of the grounding system, potentially leading to unsafe conditions. When installing a bare copper grounding conductor for direct burial, several factors must be considered to ensure proper installation and long-term performance. Firstly, the depth of burial is important. The National Electrical Code typically specifies a minimum burial depth for grounding conductors to protect them from physical damage and corrosion. Secondly, the type of soil can affect the corrosion rate of the copper conductor. In highly corrosive soils, it may be necessary to use a larger conductor or to provide additional corrosion protection. Thirdly, the connections to the grounding electrode system must be made properly to ensure a low impedance connection. This typically involves using approved connectors and methods for joining copper conductors. The grounding electrode system typically consists of one or more grounding electrodes that are electrically connected to the building's electrical system and to the earth. Common types of grounding electrodes include ground rods, ground plates, and concrete encased electrodes, also known as UFA grounds. The purpose of the grounding electrode system is to provide a low impedance path to earth for fault currents, which helps to stabilize the voltage to earth during normal operation and to minimize the risk of electrical shock during a fault. The National Electrical Code provides specific requirements for the installation and sizing of grounding electrode systems. These requirements are based on factors such as the size of the building's electrical service, the type of soil, and the desired grounding impedance. Compliance with these requirements is essential for ensuring the safety and reliability of the electrical system. In addition to the minimum size requirement for the bare copper grounding conductor, the National Electrical Code also specifies other requirements for grounding systems. These requirements cover topics such as the bonding of metal enclosures, the grounding of equipment, and the separation of grounding and neutral conductors. Understanding and complying with all of these requirements is essential for ensuring a safe and effective grounding system. It is important to consult the latest edition of the National Electrical Code and to work with a qualified electrician to ensure that all grounding requirements are met. Furthermore, it is crucial to understand the difference between grounding and bonding. Grounding refers to connecting the electrical system to the earth through a grounding electrode system. Bonding refers to connecting metal parts of the electrical system together to create a low impedance path for fault currents. Both grounding and bonding are essential for electrical safety, but they serve different purposes. Bonding ensures that all metal parts of the electrical system are at the same potential, which helps to minimize the risk of electrical shock. Grounding provides a path for fault currents to flow back to the source, which allows protective devices to trip and to energize the circuit. The proper installation of a grounding and bonding system requires careful attention to detail and a thorough understanding of the National Electrical Code. It is important to use approved materials and methods and to follow all applicable codes and standards. Failure to properly install a grounding and bonding system can create a serious safety hazard. Therefore, it is always best to consult with a qualified electrician to ensure that the work is done correctly. When selecting a bare copper grounding conductor for direct burial, it is important to choose a conductor that is specifically listed and labeled for this purpose. The conductor should be made of high-quality copper and should be free from defect. It should also be sized correctly to meet the requirements of the National Electrical Code. In some cases, it may be necessary to use a larger conductor than the minimum size required by the code. This may be necessary if the soil is highly corrosive or if the potential fault current levels are very high. It is always best to err on the side of caution when selecting a grounding conductor. In addition to the size and type of conductor, it is also important to consider the method of connection to the grounding electrode system. The connections must be made properly to ensure a low impedance connection. This typically involves using approved connectors and methods for joining copper conductors. The connections should be inspected regularly to ensure that they are still tight and corrosion-free. If the connections are loose or corroded, they should be repaired or replaced immediately. Maintaining a proper grounding system is an ongoing process. The grounding system should be inspected regularly to ensure that it is still functioning properly. The grounding electrodes should be tested periodically to ensure that they are providing a low impedance path to earth. Any problems with the grounding system should be corrected immediately. A well-maintained grounding system is essential for electrical safety. It helps to protect people and property from the hazards of electrical shock and fire. Therefore, it is important to take the time to understand the requirements for grounding systems and to ensure that they are properly installed and maintained. To further elaborate on the importance of the number 8 American wire gauge minimum size requirement for bare copper grounding conductors and direct burial applications, let's delve into the specific factors that influence the standard. Firstly, the ampacity of the conductor plays a crucial role. Ampacity refers to the current carrying capacity of a conductor. A grounding conductor must be able to safely carry the maximum fault current that is likely to occur in the event of a ground fault. The number 8 American wire gauge conductor has a sufficient ampacity to handle most residential and light commercial applications. Secondly, the mechanical strength of the conductor is also important. The conductor must be strong enough to withstand the stresses of installation and the potential for physical damage after installation. The number 8 American wire gauge conductor has sufficient mechanical strength for most direct burial applications. Thirdly, the corrosion resistance of the conductor is a significant consideration. Copper is a relatively corrosion-resistant metal, but it can still corrode over time, especially in certain types of soil. The number 8 American wire gauge conductor has a sufficient amount of copper to resist corrosion for many years in most soil conditions. Fourthly, the cost of the conductor is a factor. While it is important to use a conductor that is large enough to meet the requirements of the National Electrical Code, it is also important to consider the cost of the conductor. The number 8 American wire gauge conductor is a relatively cost-effective option for most direct burial grounding applications. The National Electrical Code provides detailed tables and calculations for determining the appropriate size of grounding conductors. These tables and calculations take into account factors such as the size of the building's electrical service, the type of soil, and the desired grounding impedance. It is important to consult these tables and calculations to ensure that the grounding conductor is properly sized. In addition to the minimum size requirement for the bare copper grounding conductor, the National Electrical Code also specifies requirements for the grounding electrode system. The grounding electrode system must be installed in accordance with the code and must provide a low impedance path to earth. Common types of grounding electrodes include ground rods, ground plates, and concrete encased electrodes. Ground rods are typically driven into the ground at least 8 feet and must be spaced at least 6 feet apart. Ground plates are typically buried horizontally in the ground and must have a surface area of at least 2 square feet. Concrete encased electrodes are typically installed in the footing of a building and must be in direct contact with the earth. The National Electrical Code also specifies requirements for the bonding of metal enclosures. Metal enclosures that contain electrical equipment must be bonded together to create a low impedance path for fault current. This helps to minimize the risk of electrical shock in the event of a ground fault. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that connect the metal enclosures together. The bonding jumpers must be sized appropriately to carry the maximum fault current that is likely to occur. The National Electrical Code also specifies requirements for the grounding of equipment. Equipment that is likely to become energized must be grounded to provide a low impedance path for fault currents. This helps to minimize the risk of electrical shock in the event of a ground fault. Equipment grounding is typically accomplished by using equipment grounding conductors, which are wires that connect the equipment to the grounding system. The equipment grounding conductors must be sized appropriately to carry the maximum fault current that is likely to occur. In addition to the requirements for grounding and bonding, the National Electrical Code also specifies requirements for the separation of grounding and neutral conductors. Grounding and neutral conductors must be kept separate except at the service entrance. This helps to prevent ground loops, which can cause nuisance tripping of circuit breakers and can increase the risk of electrical shock. Ground loops occur when there are multiple paths for current to flow back to the source. This can cause current to flow through the grounding system, which can create a voltage difference between different parts of the grounding system. This voltage difference can create a risk of electrical shock. To prevent ground loops, it is important to keep grounding and neutral conductors separate except at the service entrance. At the service entrance, the grounding and neutral conductors are bonded together to provide a single point of reference for the electrical system. This helps to ensure that all parts of the electrical system are at the same potential. In summary, the minimum size of number 8 American wire gauge for bare copper grounding conductors in direct burial applications is a critical safety requirement of the National Electrical Code. This requirement is based on factors such as the ampacity of the conductor, the mechanical strength of the conductor, the corrosion resistance of the conductor, and the cost of the conductor. In addition to the minimum size requirement, the National Electrical Code also specifies requirements for the grounding electrode system, the bonding of metal enclosures, the grounding of equipment, and the separation of grounding and neutral conductors. Compliance with all of these requirements is essential for ensuring the safety and reliability of the electrical system. Always consult the latest edition of the National Electrical Code and work with a qualified electrician to ensure that all grounding requirements are met. Remember, electrical safety is paramount, and a properly installed and maintained grounding system is a critical component of a safe electrical installation. The information provided here is intended for educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before performing any electrical work. Understanding the principles of grounding and bonding is essential for anyone working with electrical systems. By following the requirements of the National Electrical Code and working with a qualified electrician, you can help to ensure the safety of yourself and others. The proper installation and maintenance of a grounding system is an investment in safety that will pay dividends for years to come. Therefore, take the time to learn about grounding and bonding and to ensure that your electrical system is properly grounded and bonded. And remember, when in doubt, always consult with a qualified electrician.